The River Thames flows through the most heavily populated area of Britain. But a few years ago, it had a problem. Pollution. And it needed a mathematical model to point out the best solution. The problem came from London's sewers. All the sewage from North London was concentrated at a sewage works at Beckton. And sewage from South London was taken a little further out to Crossness. At these points, the sewage is treated in various ways to neutralise it. An important part of the treatment uses aeration. You can clean up sewage with oxygen. But all this plant costs money. So how much treatment should we use? What the sewage works doesn't treat, the river will. And that uses up oxygen from the river. Fish depend on oxygen. If the level of dissolved oxygen is high, then fish will thrive. So the presence of fish, showing that there's dissolved oxygen, indicates the health of the river. The Thames Water Authority is now responsible for checking the oxygen concentration in the river. Measurements are taken at various points, and the results are compared from year to year. The earliest measurements were taken in the 19th century. Here's a plot of oxygen concentration against distance from London Bridge. As the years passed, conditions worsened. The worst part of the river was always about 20 kilometres downstream. The 1950s were a crisis period. With no oxygen, the river was dead. A major factor in the recovery since then was the development of the mathematical model. And by 1975, the oxygen concentrations were on the way to recovery. Andrew Coburn is pollution controller for the Thames Water Authority.
Historically, we put effluent into the Thames in the hope that the flow would carry that effluent out to sea and it would be disposed of in that way. But we now know that this doesn't happen. In fact, the effluent is retained in the river by the ebb and flow of the tide, and in fact it's purified there, utilising the oxygen from the river. Now, we could in fact treat the sewage to a very high standard at sewage works on the land, but this is very expensive. And we've used the mathematical model to determine the best way of doing things, how much treatment to give it on the land and how much to allow the river to do it itself.
So, decisions were taken using a mathematical model. But how? Well, in this programme, we're going to follow through the development of a rather complicated mathematical model. We're going to follow it through in the sequence followed by the original modelers. And we're not going to concentrate on all the detailed mathematics. We're simply going to ask you to follow the train of their thoughts. Perhaps the most important thing about this model is the way in which it was built up from smaller parts. So let's see what they did. This is that 1950 crisis curve again. Here is the concentration of dissolved oxygen expressed as a percentage of saturation. That is, a percentage of the maximum amount of oxygen you could get into the water. And here's the distance measured in kilometres from the centre of London out towards the estuary. And you see that for a large stretch of the river, there was either no oxygen or next to no oxygen. The river was, in fact, dead. So that's the problem. But if you were trying to construct a mathematical model of a river, where would you start? Well, to see some of the factors involved, we've got a physical model in the studio. And perhaps you can begin to think now of some of the factors that you have to take into account in the mathematical model. For instance, the water coming down from the tributaries produces a general flow of water out towards the sea through the estuary. And then, of course, there's the tides. And we certainly shouldn't ignore them, because any particular bit of water in the Thames may be carried up and down the river up to 15 kilometres between the flow and the ebb of the tide. And of course, right at the centre of the whole problem is the sewage works, which is really the thing that's causing all the trouble. Now, a consequence of all that is that you can't consider that one bit of the river will be the same as another bit. You can't think of the river as one large uniform pond. But perhaps if we can't think of the whole river at once, what we should do is think of a bit of the river. If we put in two partitions like this and isolate a particular segment of the river, then maybe that will help us with our mathematical modelling. Well, it helps us in that we can forget all about the rest of the river and concentrate on this particular segment of it. And that's what the original modelers did. They divided the river up into imaginary segments in this sort of way and thought first about the behaviour of oxygen and pollutant in a particular segment. So, that's what we're going to do. Let's think about this segment, which contains a certain amount of water with a certain concentration of dissolved oxygen and, initially, a certain amount of pollutant. What now happens? In the water, there's dissolved oxygen and pollutant. Some of the oxygen acts on the pollutant, producing harmless compounds and reducing the oxygen. So what happens in our section of the river? We start with a certain amount of pollutant and oxygen. Experiment shows that the reactions slow down as the pollutant is used up. We can plot pollutant level against time. And we get a graph like this. So now we know something about what happens in that particular segment. A segment which has initially a certain concentration of oxygen, a certain amount of input of pollutant initially, and then is a closed system. But what was the mathematics involved? Well, here's the first equation, which relates the amount of pollutant at time t by a differential equation which says that the rate of change of the amount of pollutant is proportional to the amount of pollutant, this Kp being just a constant. And it's a decrease, hence the minus sign. And it's a differential equation that you might recognize because it has exactly the same form as the differential equation we used in that program about drugs, the drug theophylline. The oxygen equation, though, is slightly different. It relates the amount of oxygen at time t to the amount of pollutant at time t. And again, there's a constant in here. Well, those two equations are not very difficult to solve, but we're not going to solve them in the program here. Instead, we're going to look at the form of the solution. That is, we're going to look at what they predict for the way in which the amount of pollutant and the concentration of oxygen will change with time. First, the pollutant. We start with a fixed amount of pollutant, and after a period of time, this drops to 0. This solution is the familiar exponential decay. Let's see it again, this time adding a graph to show the change in oxygen concentration with time. The oxygen curve is shown as the dotted line. You can see the oxygen concentration drops as the pollutant is neutralized by it, finally reaching a steady state when all the pollutant is used up. So this is the form of the mathematical solution of our simplified problem. And we're assuming that we haven't reached a crisis stage where the amount of pollutant is such that it uses up all the oxygen. The amount it does use up in taking the oxygen concentration from this level down to this one here, of course, depends on the initial input of pollutant. So what we want to do first of all is to look at the way that that final oxygen concentration is related to the initial input of pollutant. Let's have a look at that. As you might expect, if the initial amount of pollutant is higher, the final steady state of oxygen concentration is lower. And if the initial amount of pollutant is lower, then the final steady state of oxygen concentration is higher. And if we don't put in any pollutant, then the oxygen concentration stays at 100. So, with a fixed initial amount of pollutant, which uses up oxygen in order to get rid of it, this is our mathematical solution. It's a solution, if you like, for a pond with a certain amount of pollutant dumped into it. But it's not, of course, a solution which could apply to the whole river. And even for a pond, it wouldn't be an adequate solution. Because a pond has a surface in contact with the air, and when it's in contact with the air, oxygen is being absorbed into the surface all the time. And so our model has to be elaborated. We have to include an input of oxygen into the surface which is happening all the time. And that, of course, affects our equation. And in our equation for oxygen, we've got an extra term which represents an input of oxygen from the surface. Now, we're not going to look at the mathematical form of that, although it's not really very complicated. But of course, the problem is really about oxygen and pollutant. And this effect of absorption of oxygen on the surface means that any once and for all dumping in of pollutant would actually be cleared by this absorption of oxygen, and ultimately you'd get up to 100% oxygen in the water again. The real problem comes because, in a thing like the River Thames, we have a continuous input of pollutant. So we've got another factor in our model, which is this continuous input of pollutant. And that gives us another term, this time in the pollutant equation. There is a sewage inflow. Now, these are two slightly more complicated equations. They're a bit more difficult to solve, but we can solve them. But we're not going to look at the forms of the mathematics. We're simply going to look at the sort of solution you get if you assume a continuous sewage inflow and an absorption of oxygen at the surface. And this is what those solutions then look like. Again, we start with a certain amount of pollutant and a certain initial concentration of oxygen. After time, they both tend to steady states. In fact, in reality, it takes about a couple of weeks. As before, the continuous curve represents the amount of pollutant and the dotted curve the concentration of oxygen. And you notice that the amount of pollutant levels off at some steady state which is certainly not zero. So this now is the form of the mathematical solution of our more complicated problem here. Let me remind you that what we're interested in are the steady state levels of the concentration of oxygen and amount of pollutant. And I want you to think, first of all, how those might be changed by the initial concentration of oxygen and the initial amount of pollutant. Look then, when we change those, at these two and at the levels that we get here. If we alter first the initial concentration of oxygen, and then the initial amount of pollutant, you see that neither of them affects the steady state values. And that's interesting. It means that the steady state values that we're arriving at here are not dependent on these initial conditions, but must be dependent on, well, the rate at which oxygen is being absorbed at the surface, the rate at which the sewage is flowing in, and the rate at which these two are interacting. Now, since we can't do anything about the input of oxygen at the surface, perhaps we should look at the way in which conditions change when we change the rate of sewage inflow. Suppose we increase the rate of sewage inflow into the segment. Well, as you'd expect, the steady state concentration of oxygen goes down, and if we reduce the sewage inflow, the steady state concentration of oxygen goes up. What we're changing here is the rate of sewage inflow. And while this does have some effect on the steady state level of pollutant, the important effect is on the steady state concentration of oxygen in the segment. If, for instance, we want to keep the oxygen level above some critical value, then there is a limit to the rate at which we can put in pollutant. So we now have an adequate mathematical model and the solution for a pond which may contain initially a certain amount of pollutant and may have a continuous inflow of pollutant. And this is the solution. But of course it's not the solution for the whole river. The river, if you like, consists of a lot of ponds joined together. However, maybe we can make a bit of progress. If we think of that segment of the river next to the sewage works, then it is receiving a pollutant input. And so the appropriate solution to the mathematical problem is this solution. And after a certain length of time, we can estimate that the concentration of oxygen will fall to this steady state value. And if we take that and put it at the appropriate place on the river, measuring distance along the river here, say there, where the sewage works is, then we have that level of oxygen concentration just at that point. And of course at every other point where there is no input of pollutant, then the concentration of dissolved oxygen is at the maximum of 100%. But that doesn't look awfully like the sort of sag curves that we saw before, which look much more like that. And I think the reason is fairly obvious. We've got the river divided up into segments, and they are completely separated from each other. There is no interaction between these segments, and yet these ponds, if you like, are joined up. Now that interaction is really quite complicated, and the mathematics gets a bit complicated from now on. So concentrate from now on simply the way in which the modelers put in the various factors. To think again about the other factors that are involved, let's go back to the physical model. This time, let's look at three segments. This one is right next to the sewage works and so has a pollutant inflow. And these two have no pollutant inflow. But at the moment, they're separated. Let's see what happens when I take out the partitions between the two. And you can see that there is a mixing between the various segments. If there is pollutant in this one and no pollutant in the others, then there will be an interchange which will tend to equalize the three segments. Here's one such boundary. There's a continuous movement from the left segment to the right, and an equal movement from the right to the left. These movements cause a mixing which spreads through each segment. In addition, there's a downstream river flow. And the mixing is now no longer symmetrical. And there's one other major factor that our mathematical model has to take into account. We're considering a section of the Thames which is tidal. And so far, our model has completely ignored that. And that's rather serious when you think that any particular bit of water may be moved down the river and up again through about 15 kilometres between high tide and low tide. Well, the original modelers didn't forget that, and they took it into account in a very ingenious way. Instead of thinking about the segment of the river opposite a particular point of the bank and having to worry about flow in and out of that, they took segments of the river which moved up and down the river. And the effect of that is only to change the sewage inflow. When a particular segment goes past the sewage works, it gets an input of pollutant. And as it comes back, when it gets to the sewage works, it gets another input. And for the segments, it's just as though the sewage works itself were moving back and forth up the river, putting pollutant into several segments. And for any particular segment, producing an intermittent input of pollutant. Now, we haven't tried, of course, to introduce in mathematical form these flow and tidal factors into our model. But the original modelers did, and when they did that, they produced a sag curve like this grey one here. And then they did the right thing. They compared it with reality, in other words, with the measurements. And that was the actual sag curve, the white one. And you can see that there is a pretty good comparison. That's the 1950 curve. But they got similar good fits for other years. And one of the features of this model has been the closeness of the fit of the results of the model and the actual observations. They were working in the 1950s on this. But this model has been updated since then, but essentially it's the same model. And it's still very much in use. To finish the story, Andrew Coburn is going to tell us something about the way in which the model is still being used now.
We're using the model to consider any developments that take place. The population of London is shifting, and in fact we're having to build new sewage works further out, such as a new one we're planning at Long Reach.
And what does it all cost, this?
Well, this new sewage works we're building out to the east of London, we've had to consider that on the model, and what we found is that by spending £5 million we can increase the minimum of the sag curve from 20% to 30%. But by spending a further £3 million we could only raise it a further 2%. And we've decided that to stop at the £5 million mark.
That's where you've got to stop. But that 30% will allow fish like salmon to get up the River Thames.
Oh yes.